problem statement is about the need to assess the performance and sustainability of geopolymer concrete in pavement constructions compared to ordinary Portland cement. Theory in engineering. To solve the engineering problem and several advantages over the conventional concrete. First, environmental benefits. Second, improved strength and durability. Third, reduce crack and shrinkage. Fourth, high temperature resistance. Fifth, versatile application. Geopolymer concrete revolves around using an alternative binder materials called geopolymer. Geopolymer can be activated by alkaline solutions. Activation process form three-dimensional polymetric networks that provide binding properties to cement. Geopolymer binder, used in geopolymer concrete as an alternative to ordinary Portland cement OPC, formed by a chemical reactions between aluminum silicate, which is rich materials, and alkaline activator solution, resulting in geopolymer gel, act as a binding agent, offer lower carbon footprint and utilize industrial byproduct, provide high strength, excellent chemical resistance, and enhanced fire resistance, improve durability and has a longer service life compared to the traditional concrete, promote sustainability and reduce environmental impact in construction. Alkaline activations. Essential step in geopolymerization process of geopolymer require alkaline activated solution to initiate and sustain chemical reactions. Activated solutions include alkaline hydroxides such as sodium hydroxide or silicates. Activator provides necessary alkalinity for reactions. Reactions occur between aluminum silicate source materials and alkali, form geopolymeric gels as binding agents. Crucial for achieving desired properties and performance of geopolymer concrete. Type and concentrations of activator influence product characteristic. Control and optimizations important for desired strength and durability. Enable utilize of alternative materials and reduce reliance on cement-based binder.
Chemical reaction. Geopolymerization is a complex chemical reaction used in geopolymer concrete. Source material dissolve or re-participate in the presence of the N-alkali activator. These forms are three-dimensional geopolymer gel network that act as a binding and the hardening agent. Chemical interaction with the alkaline activator leads to the strong bond in formation. Curing process further transforms the geopolymer gel, resulting in hardening and the disparate properties. Factors like source material composition, alkaline activator, type and concentration, curing condition, and time influence the reaction. Geopolymerization allows for the use of dissolved source material, promoting sustainable construction material. Properties and performance. Geopolymer concrete demonstrates a range of desirable properties. It has built high compressive strength comparable to or even exceeding that of the traditional Portland cement concrete. Geopolymer concrete has low permeability, making it more resistant to the water penetration and reducing the risk of deterioration. It offers excellent chemical resistance, making it suitable for environment with exposed to harsh chemical or corrosive substance.
And result of geopolymer concrete based on case study. Firstly, compressive strength test. It is done to determine the strength properties at various ages. The strength based on the test in 30 days is determined to be higher than the estimated compressive strength. Next, splitting tensile strength. It is measured to assess its resistance to tensile force. The direct tensile strength of the geopolymer concrete based on the test is determined to be 4.3 megapascal. Properties of geopolymer concrete. To begin, geopolymer concrete can achieve high compressive strength comparable to or even higher than ordinary Portland cement concrete. Furthermore, geopolymer concrete exhibit excellent resistance to chemical attack, fire, and sulfate attack, making it a durable material. Next, the workability of geopolymer concrete can be adjusted by modifying the mix design and using superplasticizer to achieve the desired consistency. After that, geopolymer concrete typically has a shorter setting time compared to OPC, which can affect the handling and placing of the material. Finally, geopolymer concrete has lower carbon dioxide emission and contributes to sustainable construction practices by utilizing industrial byproducts. Design procedure of geopolymer concrete. Firstly, material selection. Determine the source material for geopolymer concrete, such as fly ash, slag, or silica fume, based on availability and desired properties. Next, mix design. Optimizing the mix proportion of geopolymer concrete, including the ratio of source materials, alkaline activator solution, aggregates, and additive to achieve the desired strength and workability. Then, activator solution. Select the appropriate type and concentration of sodium or potassium silicate solution as the alkaline activator to initiate the geopolymerization reaction. Finally, curing condition. Design the curing conditions including temperature and humidity to promote the development of strength and durability in geopolymer concrete.
The adaptation of geopolymer concrete in construction faces challenges and barriers, including technical, regulatory, economic, and supply chain issues. Second, extensive research has been conducted on the mechanical and durability performance of GPC, highlighting its technical soundness as a construction material. Third, the study focuses on a large-scale demonstration project of GPC in highly visible and heavily trafficked locations to assess in a long-term performance and promote its use in mainstream construction. The construction of GPC pavement is efficient installation despite minor weather disruptions. Next, needed to develop chemical admixtures that enhance the flowability of GPC, improving its handling and placement during construction. The strength development of the GPC pavement over time was observed, with significant increases in strength from the time of a road reopening to 597 days after placement. The performance of GPC pavement, including its resistance to deterioration and abrasion, was comparable to adjacent ordinary Portland cement concrete pavement. Lastly, the findings contribute to building confidence in GPC as a durable and sustainable construction material, supporting its potential or widespread adoption. The successful implementation of GPC in a high-traffic location demonstrates its potential as a sustainable construction material. The GPC pavement exhibited good strength development and performed comparably to ordinary Portland cement concrete. Further monitoring of the pavement at 3 years after placement is recommended to assess its long-term performance. The successful implementation of GPC in a high-traffic location demonstrates its potential as a sustainable construction material. The findings support GPC as a viable and low-carbon alternative to conventional concrete, offering potential benefits in terms of